think it's good. Okay.
Okay,
So sorry.
thank you. And thank you everyone for sticking up for the last talk. I'm Adriana Valio from the Center for Radio Astronomy and Astrophysics Mackenzie. And in case you're wondering, that's in São Paulo, Brazil. Okay. And this is the work that my postdoc Fabian has been working on. And I'll try and be very brief, not to stay in the way of the census of the San Diego Zoo. Well, I don't need to preach to the choir here. Star spots, regions of intense magnetic fields on the sun. And here in this talk, briefly, I would like to propose a new method to estimate magnetic fields from star spots. Now, everybody's been talking about the ZDI and all the other forms of, but here I'd like to talk about how can we estimate magnetic fields of star spots using planetary transit mapping. And of course, that's only been possible from these high precision missions like Corot, Kepler, and TESS. And ZDI only works for rapid rotators, and I'm going to be talking about stars that have a rotation period larger than 5. And what is basically this method is that when a planet transits a star, it might occult a spot on the surface of the star. And when it does that, it generates a bump on this transit light curve. And by modeling this, we can basically estimate the size and the intensity of the spot. So our goal then was to, how can we do this? So we go back to the star that we know very well. This is a solar magnetogram. And what we're going to do is we're trying to find relations between the sunspots, magnetic field, and their properties like sizes and intensities. And we're going to then apply this relation to 14 solar type stars and M stars that we have obtained the properties of the spots through transit mapping. And here is what it, so we did a study of over 32,000 spots, sunspots from the sun, using SOHO data, white light, MDI images, and magnetograms for solar cycle 23. And we obtain we can obtain two independent relations of the magnetic field of sunspots with its intensity or with its area. Here is with intensity, just one plot here, this relation here, and this relation is this red line. But we know that in the case of modeling the star spots, there is a strong degeneracy between the spots area and intensity. And so what we've done is we estimated we defined a quantity called spot flux deficit. That's how much flux the spot subtracts from the stellar photosphere, which is just the area of the spots multiplied by 1 minus the intensity of the spot. And so here are the 32,000 suns or more sunspots, and then we just did a linear fit here to the data, obtaining this relation. So this is the relation that we are going to apply to the spots on the of the stars. And so here are the 14 stars, and there are 17 planets at all. You can see here the spectral type, ages. I mean, there's stars of different ages, rotation period, and sizes. And most of the planets are gas giants, but there are some which are Earth size. This is Earth size here. Okay, so this is the model. It's called Eclipse. It can be obtained from the GitHub here. And in 2003, I was the first to propose this method that you could get, like estimates of the spot parameters, like from these kind of bumps that we see on the transit light curve. And as I mentioned, the height of the bump will give you a measure of the intensity, and the width of the bump, a measure of the radius of the spot. And I mean, it's a 2D pixelized image of a limb darkened star. And there are many things you can do with this. You can put rings in a planet, moons, etc. But moving on. So here, from these 14 stars and from the transits of their 17 planets, we were able to map 2,269 spots You can see that some of them have very few spots, but like Kepler 17, there was over 1,000 spots. And we only model, of course, the signals that are above 3 sigma of the residuals. And here we apply them to those over 2,000 spots, that relation that we obtained, the linear relation from the sunspots. And so here are the 14 stars color-coded for the histograms of the magnetic field. Of course, each star has a different, like distribution, but basically the takeaway from this is that the spots, the star spots magnetic fields obtained this method, it's a very simple method, range from 2,500 to 4,000 watts. And of course, here we're only looking at the strongest spots or maybe active regions on the surface of the stars, right? We don't have the sensitivity to map very small spots, probably just the bigger ones. And these are not different from what we get from sunspots. And here is the relation of the magnetic field of the spots with their intensity at star spots and or with their area or logarithm of the area. And what we see is that there is an anti-correlation with the intensity and a positive correlation with the area, not surprisingly, right? This is what the flux deficit relation dictates. But basically what we see is that darker and larger spots exhibit stronger magnetic fields, which again is what we see on the sun. And here, just very briefly, to try and correlate with stellar parameters. So we found that here is on the y-axis is always a star spots magnetic field in thousands of gauss, in kilogauss. And here is the stellar effective temperature and rotational shear, magnetic shear, I'm sorry, delta omega. And we see there is basically no correlation here with those parameters, stellar parameters. However, we see as a weak anti-correlation with the stellar H or the star rotation period, which is something that we've seen in many talks today, right? These are all stars to see, the period is, for the stellar periods are above 5, higher than 5 days. And so these are all in the unsaturated regimes. Here's the sun for comparison, this black dots. So, well, I think I said everything here. And this is again what you expect, like for rotation that follows the splenic knob. And so, well, I guess I really did hurry. So here are my conclusions. So we propose a very simple method to estimate star spots magnetic field using a relation that we obtained from the sun. And what we found was that darker and larger spots have stronger magnetic fields. The magnetic fields are in the range of a few kilogauss from 2,500 to 4,000. And of course, we're only mapping the strongest spots or the more intense ones. And we didn't find any correlation between, and as for the stellar properties, we didn't find any correlation of the spot's magnetic fields with the effective temperature or mass of the star, and neither did we find any correlation with the magnetic shear. However, we did find a weak anti-correlation with the stellar rotation period for its age, which follows. Okay. And that's it. Thank you very much.
You forgot something.
That's supposed to be my first line. I would like to thank the organizer.
It sounded like fishing at these questions.
Steve, sorry. Have you seen the poster by Bhatia, I think? They did some 3D MHD models of star spots, and I think if I interpret works, there's very good agreement with your results.
Really?
I mean, with the general results. So I mean, take a look at that. It's a nice confirmation.
Okay.
Any other question before we all run out?
One from here.
One from here, yes. Oh, It says, thanks for the talk. Star spot contrasts are likely very different from G2 to K0 and to M0. How solar-like in TF was your set of stars because you base the relations to star spots?
Yes, yeah, I mean, we don't have much to work with, right? It's 14 stars. It's not easy to find, what to do the transit and everything for these stars. But I mean, if we can assume here that, like the effective temperature, so has to do with the spectral type. But you can see that we have like, well, this is the sun, okay? But yeah. So we have these two stars, the interesting thing here, which I didn't mention, but due to the lack of time, is that these two stars are the only ones which we know have flared. Not that the other ones didn't flare, they didn't flare during the Thoreau or the Kepler observation. These two did. So, and they have the smallest magnetic fields. But yeah, I mean, we do have, like from all this, all the spectral classes, and we don't see much difference according to spectral types.
Great. Okay, well, thanks a lot. Again, thanks. We're running a little late and I'm very impatient with this. So I guess we can try to see that and do have more questions.
Very excited. You have any?
I guess I'll let you grab the computer.
Thanks so much.